So good afternoon. I'm very happy that I can meet you again. It is our third meeting in the framework of this course, Mathematics for Machine Learning. And today I'm going to talk about calculus, about functions, and about derivatives. And of course, mainly about applications of derivatives, of functions in machine learning. Yesterday we talked about linear algebra and about some ideas which are very useful in data analysis, for example, for analysis for reduction of the number of variables. But today, topic is completely different. Today, we will be talking about functions. So as usual, I'm going to share my screen. It is a notebook for today. And of course, at the beginning of this document, I attached libraries, packages, which I will use during calculations. So you see that I'm using Matplotlib library for graphical presentation of data. And also, for me, today, very important part, it is a very important tool. It is a SymPy library. It is a library which we use for symbolic calculations. When we are going to perform some operations on symbols which we have in different formulas. We will see, because I'm going to show you some examples, how to use these tools. Functions. Functions, it is our main topic for today. Function, it is a description of relationship between input variables and output variable. Function has only one output value. So it is a description which has a form of a formula. And for each input, we have one corresponding output value. But of course, the same output value may correspond to many different input values. Functions may be represented in different ways. For example, using formulas, using graphical presentations. We can have functions with one input variable or with many, more than one input variables. But today I'm going to talk only about functions which has one input variable. So our functions which we will use today will have this form which we see here. It will be a description of the transformation of value of variable, where x, it is our input variable. For example, here we see an example. We want to transform x value in this way, which is represented here, which is defined here. So I'm going, during this transformation, calculate the second power of x. X to the second power, x squared. Of course, it is only. And in this way, we will calculate an output value. Very often, this output value is represented by y symbol. So we can define functions in this way, functions of a single with a single variable, or in this way. So I think that you know about all these issues because they are discussed in primary school, I think. We can perform some calculations, some operations using functions. And also we can do it everything using Python language. Also there is in Python some tools which we can use for defining functions and for performing some operations on functions. Of course, now I'm thinking about mathematical functions, because we know that in Python language, we can define functions which describe some operations which we are going to perform during program realization. I think about mathematical functions. These mathematical functions can be represented in Python in very easy way using SymPy package. So therefore, I use this instruction here to import this package, to attach this package. And here I use this package for define a function. A function is here. F is defined, this function F is defined in this way, which we see here. It is x to the second power minus 3. So it is a function definition. Function in mathematical sense. In this definition, I use x as a symbol. Therefore, first I must declare that x is a symbol which I use in expressions which will be used in this program for function definition. So first, I defined x as a symbol, and after it, I use this symbol defining a function. It is necessary to define this object as a symbol because we will make some operations on function definition using symbolic operations. Therefore, it must be defined as a symbol. So our function is here, and here I use plot function, but plot function from this SymPy package to present this function graphically. So we see this function here. And here we see all these features which I mentioned earlier. So function, it is a description of relationship between variable x, which is represented by this horizontal line, and value y, which is represented by this vertical line. The description is here, and graphical presentation of this description of this relationship we can see here. And we see that for every input value, input values are represented by x-axis. We have one output value. We can, of course, using this graph, guess, maybe not exactly, but approximation of this output value for every x value. But for the same y value, we can have many x for the same for the same y value, we can have many x values. For example, for value 10 here, we have value about 3 point something and minus 3 point something. So we have two x values and for them, the output value, y value is the same. So it is very, very simple example. Here we have sine function, also very well-known function. So I use this function to define the plot. We're talking about functions, and for me, some features of functions are very interesting, useful from the perspective of machine learning. And one of the first feature which I am going to discuss is related to 0 points of a given function. For every function, for example, for this function, we can define 0 points. 0 points of a given function are defined by x values, and x we must have the value of this function equal to 0. Or we can define 0 points in this way, which we see here. 0 points of a function are points where the graph of the function crosses the x-axis. Or 0 points of a function are points for which the value of this function is equal to 0. So y value corresponding to this x values is equal to 0. So the interpretation is very, very easy. We know how to interpret 0 points. And knowing a function, very often we want to calculate 0 points. What we should do? If we want to calculate 0 points, we should solve the equation, which has this form, which we can see here. So this function is equal to 0. It is our equation. And we must find x values for which a value of this function is equal to 0. So we must solve this equation. And how to do it? For example, we have a function which is defined here. X to the second power minus 3. We can here to find 0 points. If we want to find 0 points, we should solve the equation. This function is equal to 0. So in our case, this equation is x to the second power minus 3 is equal. And we want to solve it. Of course, not manually, because we have Python language, and we are going to use this SymPy package for symbolic calculations. And solving equations also to symbolic calculation. And we can try to do it. First, I'm going to define this equation. Equation is defined by defining 2 elements. The first one, it is an element which we have on the left side of this equation, and the second parameter, it is an element on the right side. So this function was defined here, and we want to solve the equation that this function is equal to 0. And here I printed this equation here, so we see x to the second power minus 3 is equal to 0. I'm going to solve this equation. So I use this solve function for solving this equation. This equation, which is defined here as the first parameter, this equation was defined here. And as the second parameter, I must define an object which I use as an unknown value. So in my case, x represents an unknown value. And I was solving it, and the results I assigned to res object. And I printed it. So you see here that we obtained two results: minus square root of 3 and plus square root of 3. Minus square root of 3 is here, plus square root of 3 is here. So of course it is a solution which was obtained using symbolic calculations. So it is not numerical, but it is a symbolic calculations. And these results were printed here, and the last command is a command which I use for displaying this chart, this graph. So we see that everything is okay. 0 points of this function f, which was defined here, we can see here minus and plus square root of 3, and also we can see here these results. So we know how to solve different equations, because of course we can define different functions and we can solve an equation. So please try to use this package for solving many equations, different equations, and to try if it is easy or not. So we know this concept of 0 points of functions. Next very important concept is related to functions. It is difference quotient. Difference quotient is defined here. This formula is maybe complex, but the idea is very, very easy. I try to show the idea of difference quotient here. We have a function. This function is represented here using this maybe not yellow, but something between yellow and brown line. This yellow line here was used to presenting this function. And I calculated a value of this function for x equal 0.5. Is here, and the value is here. And also for x equal to 3. And this value is here. So I calculated values of this function for two different input to x and value x plus h. It is here. And I calculated difference between these two values. Therefore, we have in this name of this concept difference quotient, but difference means we have here. So the difference is related, is represented here by this vertical line. It is a difference between values of this function for x and for x plus h. And here, this horizontal line, has this label h attached. It is a difference between these two arguments. And difference quotient means relation, is defined here. So I should divide the length of this line, this vertical line, this line. And in this way, I can calculate the value of this difference quotient. And so the way in which we can calculate this value is very simple. We should calculate these two differences and divide one value by the second value. But what is the interpretation of this value? We can see here a triangle with one angle which is equal 90 degrees. So in this triangle, we can divide lengths of this part and this part, and in this way we can calculate tangent value of this angle which we have here. So if we please look at these two black dots. They represent values of this function for x and x plus h. And here we can, and next we can draw this line, which crosses these dots and crossing axis in this point. This line, which crosses the graphical representation of this function, is called secant. It is a secant line. And we want to calculate the measure of this degree which we have between the secant line and x-axis. The measure of this degree which we have here. How to do it? The tangent of this degree is equal to this difference quotient, because we can calculate this relation, so the length of this vertical line and this horizontal line, and in this way we can calculate a tangent value for this angle. So using this formula, we can calculate the slope of this line, which we can see here. And this value is named difference quotient. And also, this concept is very useful and very important when we want to define derivatives. Sorry, it is here. I see. And my mistake. Derivative. Here you see some definitions of derivatives. Derivative. It is the limit of the difference quotient as the h value. Maybe also I will change it. Or maybe not, because in this formula I have this delta x value approaches 0. This delta x is equal, which we have here, is represented by H letter here. Sorry for it. So derivative of a function, it is the limit of a difference quotient as the value delta or value h approaches zero. Approaches zero, it means it's very, very small. So please think about the situation which we have here on this picture. We have value h here. It is equal about 1.5. But what happens if this h value is very, very small? 0.00001. Then, in this situation, the slope of this line, which touches the graphical representation of this function, is different. This line is here presented. This red line, we will get it if h is very small. So here, for this situation, which we see here, h now is rather big. And of course, we can divide lengths of these green lines, and we get tangent of this angle, as I said before. But now please decrease this h value. What will happen if it is smaller? And what we get if it is very, very small? Very, very small. So we are going to calculate a limit in the situation in which x is very close to zero. It is represented by the symbol. What will happen if delta x here is very, very small? This value will represent a tangent of this angle, and this value is called derivative of this function f. So the graphical interpretation of a derivative, it is an tangent of a line which touches the graphical representation of this function. It is a value of the derivative in this point. So when I want to calculate derivative for this x value, I have two possibilities. The first possibility is to decrease this this h value, to decrease it, to make it very, very small, and calculate the quotient of the situation. But sometimes it may be difficult. And the second approach, for this very small h value, we can draw this straight line, and we can measure the angle which we have between this line and x-axis, and calculate a value of tangent for this for this angle. It is a derivative of a function in this given point. So we see that these two terms, difference quotient and derivatives, are very strongly connected. The derivative, it is a limit of a difference quotient for delta x, or for h value approaches zero. For this x or delta x or h value, which are very, very close to zero value. So it is a definition, but interpretation, graphical interpretation is related to the tangent of the angle between this line which touches this function and x-axis. So we know the definition of a derivative of a function. Of course, we would like to have a formula for calculating a value of this derivative in a given point. So we want to have for our function, we want to define a formula, a function, which we will use for calculating a value of a derivative of this function in a given point. And we can do it, we can define this function using also Python language. Here we have a very simple example. We have a function f, x to the third power plus x to the second power minus 5 multiplied by x minus 2. So this function is here. And here, this graph, we see this function. This function is represented by this blue line. So f function is here represented by this blue line. And I calculated a formula which I can use for calculating a derivative value for every point, a derivative of this function for every x point. If I want to do it, I can use this function diff. This function diff we can use for calculating a function, for defining a function, for finding a function, describing derivatives. So I want to find the first derivative of f function. And also define x, it is a parameter of this function. And the result I assign to fd object. And this object here we see. So a function which I can use for calculating a value of a derivative for this f function is here. 3 multiplied by x to the second power plus 2 multiplied by x minus 5. So it is a function which I can use for calculating the derivative values for this f function, which I had here. And on this graph, I presented these two functions. Blue function, blue line. It is here. It is represented by this orange line. So for every x value, we can find a value. These values are represented by this blue line and values of its derivatives at every point. And these values are represented by this orange function. Here we can see all these informations. Here I use Python language and SymPy package for calculation which defines the derivatives. But of course, I can do it manually using formulas. There are a lot of formulas for calculating derivatives. Some for simple functions, there is no problem with calculating derivatives. But when we have complex function, it is difficult to calculate derivatives. And I try to find some rules which we can use when we want to calculate derivatives manually. The main rules are here. Here we see a definition of our function, and here we have the function describing derivatives for these functions which we have on the left side. So if our function is very simple, for example, y is equal to x, the derivative is 1, always is 1. When we have a constant function, the derivative value is always 0. When we have x to the second power, the derivative is 2 multiplied by x. If we have x to the third power, the derivative is represented by the function 3 multiplied by x to the second power. Generally speaking, if we have x value to the nth power, the derivative is calculated using this formula. So this n value we should move here, and here we should decrease a previous value by 1. So the derivative for this element is always equal to this element. And for some functions, derivatives. In this table, we have defined derivatives only for very simple functions. In practical applications, we have very often functions which are built with many elements, and then we should use some rules when we want to calculate derivative or the derivative function. For example, if these rules which we have at the beginning, these 3 rules are the same as I mentioned here, but here it is a sum or difference of functions when derivative for this sum or difference is equal to the sum of or difference of derivatives. Product rule. It may be interesting. We have a function which decomposed can be presented as a product of 2 other functions. Then the derivative is defined in this way. So it is a product of 2 functions, so we should calculate this value. The derivative of the first function multiplied by the second function plus the second function multiplied by the derivative of, plus the first function multiplied by derivative of the second function. If we have a relation of 2 functions, then derivative is presented in this way. Also, we can have this type of expressions when we have outer and inner functions. Then derivative of it can be calculated using this formula. It is the derivative of the outer function multiplied by the derivative of the inner function. Of course, I know that it is necessary to make many exercises, to practice all these rules when we want to calculate manually, when we want to define manually functions which we can use for calculating values of derivatives for a given function. But of course, we can do it manually using these rules we have here. This, or you can use this SymPy package when we want to, and we can try to calculate it. It works for many functions, for all simple functions. It works without problems. Maybe sometimes we can have problems with very, very complex functions, but generally it works. Maybe I'm sure that it is not the best product for a symbolic calculation of derivatives, but for many applications it is very good, and also for teaching it is very good, and it is enough. This package SymPy or other packages in Python is free, so we can, without any problems, use it for calculating derivatives. We were talking about derivatives. These derivatives also are called first derivatives, because it is possible to calculate also second, third, and further derivatives. The second derivative of a function, it is a derivative of the derivative. So we have a function, then the second derivative of this function is equal to the derivative of the first derivative. When we have f function, the second derivative can be presented in this form or this form. Also, sorry, I missed it. Also, I should said here that the derivative of the f function is denoted, is represented by this symbol or this symbol. These two symbols are equivalent, and in some books, in some papers, we can find this. In some, we can find this symbol. So we see for the first derivative, we use the same letter here, which we have in the name of the function, f, and here this apostrophe, one, because it is the first derivative. Or we can this first derivative present in this way, so it is similar to a it is similar to relation of these two values, fraction of these two values, and in the numerator it is and after it the name of this function f, and here delta, and the name of a variable which is using this function. For the second derivative, symbols which we use for representing these values are here. It is the name of this function, in this case f letter with two apostrophes, or this fraction, and this fraction here as a numerator we have delta to the second power, but it is not the second power, it is the second derivative. Therefore, we have two value here, and here a symbol of this function, f, and here as denominator, in denominator we have delta letter x letter as a parameter and also value 2. But also it is not the second power, but the second derivative. So if we want to calculate the second derivative, we can use the same rules which we can use for calculating the first derivative, but we should use it to perform operations on the first derivative of the function. And examples in Python and SymPy package are here. My function is here. So we see this formula here. It is x to the third power plus x to the second power minus 5 multiplied by x minus 2. It is a function which we use in our example. First, I calculated the first derivative. It is here. So I use this diff function for calculating the derivative of x when for f function when x is a parameter. And the result was attached, was assigned to fd object. And I printed this fd object. And a formula for calculating the first derivative is here, 3 multiplied by x to the second power plus 2 multiplied by x minus 5. You can check that that derivative which we can calculate using these rules, formulas which we had in these two tables, can give the same, will give the same result. So it is a derivative, or define that he added this third parameter equal to 1, and here I said that it is the first derivative. And the result, of course, is the same. So derivative or the first derivative means the same. When I want to calculate the second derivative, I should calculate in this way, putting the definition of this function f here, and also sending the information that I'm going to calculate the second derivative, and it is fd2 object, fd2 object, and the second derivative is here, or I can calculate the first derivative, but now I use the first derivative as a function on which I'm going to perform these calculations. We see that they are presented by other for various expression multiply. We have this expression in parentheses, but of course we can multiply it, and then we have 2 multiplied by 3, it is 6 multiplied by x plus 1 multiplied by 2, it is 2. So these two expressions are equivalent. So how to calculate the first derivative, how to calculate the second derivative for a function. Maybe these topics are interesting, maybe not are interesting, but when we are thinking about machine learning, they are very useful for us. And majority of algorithms which we use in machine learning is based on this concept. Why? Because during learning process, we try to minimize a criterion function. We want to find parameters for which a value of a criterion function is the smallest or the biggest. So we are going to minimize or maximize a criterion function. Very often we can hear about it. I think that much more often we hear about minimizing criterion function. Because criterion function very often describes errors, mistakes, and we want to find parameters for which this error value will be the smallest. Therefore, we are going to minimize it. But of course, in machine learning, models are very complicated, are very complex. And these functions which we use for describing, for defining errors or mistakes also may be very complex. And we must to minimize them. Minimize them, it means to find parameters for which we can obtain the minimal value of this function. And how to do it? Of course, there are a lot of different methods. Majority of these methods is based on this concept of derivatives. How to find a minimal value of a function, or sometimes maximal value of a function. Minimal or maximal, it means that we are going to find extremal function, extremal values. Extremum means minimum or maximum. Sometimes we are going to find minimum, sometimes maximum. Generally speaking, we are going to find extremum values for a given function. And we have here a presentation of two concepts: local and global minimum or local or global maximum. So extremum values can have local or global character. Here we have definition. A function f defined on a domain X. Domain, the word domain means a set of all values which we can use as X values, which we can use as parameters, as input values for this function. A function f defined on a domain X has a global maximum point at the point x max if a value of this function in this point x max is greater or equal to all other values of this function. Here we have is greater or equal to values of this function for all x belonging to this domain x. So it is the biggest value of this function which we have in the for all allowed values of x. It is a global. It is a global maximum. And also we can talk about local maximum. we can say that in this X max point, we have a local maximum if this value is the biggest, but only in some rather small neighborhood of this X point, X max point. Neighborhood and the size of this neighborhood is defined by this epsilon value. I think that here we see the meaning of a local minimum or local maximum. We are now talking about local maximum. So, for example, in this point, we have in this x2, in this point, we have a local maximum if this value b is the biggest for all x belonging to a small neighborhood of x2 point. This neighborhood is here, and for all values which we have in this neighborhood, this b value is the biggest. So it is a local maximum, but I'm not sure if it is a global maximum of this function, because maybe we have greater values for this function. For example, here on the right side of this chart, or on the left side. The same definition we can formulate for minimum. For example, here we can treat this A point as a global minimum. So in this x1 point, we have global minimum. It means that for all x values which we have, for all x values belonging to the domain, it is the smallest value. But here, in x3 point, we have a local minimum. Because this value, but not for the whole domain, but only for a small neighborhood of x3 point. So therefore, we can say that here we have local minimum. I don't know if these points A and B, if they are or not, because we don't know the shape of this function beyond this area which is presented here on this picture. So all these four concepts which are presented here, global minimum, local minimum, global maximum, local maximum, are defined here. And now we are going to talk how to find these minima or maxima. How to find this minimum or maximum value. How to find local extrema. We are not going about finding global extrema, because it is, generally speaking, very difficult problem. Of course, there are some algorithms which we can use when we want to find global extrema, but they are rather complex, and in general situation, it is rather difficult task. For specific functions, of course, it is possible to find it, but for many functions, it is difficult to find. So now we are talking about finding local extrema values. So how to find local minimum? Maybe first, how to find local maximum. If we want to find local maximum of a function f(x), we should check two elements. Or we should make two operations. First, we should define the first derivative of this function. And we should find points, x values, for which the first derivative is equal to 0. So first task, it is finding a definition of the first derivative function. Next, we should solve this equation. First derivative is equal to 0. And we should find x values for which it is true. And in these values, we can have local maxima. We can have, because it is necessary condition. But we are not sure. We are not sure if in these points, these local maxima exist or not. If we want to check it, we should check the sufficient condition. We should check if the first derivative at this point, for which the first derivative is equal to 0, changes its sign when it crossing this point. From positive to negative. From positive to negative. We are talking about local maximum. Local maximum. Blue, this local maximum is here. How to calculate it? First, we should solve this equation. The first derivative is equal to 0. The first derivative is represented by this yellow line. We should solve the solution. First derivative is equal to 0. It means that I'm going and points, 0 points of the first derivatives. I'm going to find points in which the first derivative crosses x axis. Here it crosses about, I think, minus 1.7 here. So in these 2 points, minus 1.7 and at 1, the first condition is fulfilled. So the first derivative is equal to 0. Here it is equal to 0, and here it is equal to 0. And when we are looking for maximum value, we should check the sufficient condition. The first derivative changes its sign from positive to negative at this point. So the first point in which the first derivative is equal to 0 is here, minus 1.7. And at this point, the first derivative changes its sign from positive, because here these values are positive, to negative, because here these values are negative. So yes, our answer is yes. But at this point, 1, the first derivative also changes its sign, but from negative to positive. Changing the sign from negative to positive is here. It's a rule which we use when we are going to find local minimum. So for local minimum, the first derivative must be equal 0. It is a necessary condition, and sufficient condition says that the first derivative changes its sign from negative to positive at this point. So using this rule, we can find these extrema values for this blue function. So first, we should solve the solution. The first derivative is equal to 0. So I should find 0 points for this yellow function. It is minus 1.7 and plus 1. And in the first case, for x equal about minus 1.7, the first derivative changes its sign from positive to negative. It means that in this point, a blue function, our function, has its maximum, local maximum, and in this point, equal to 1, the derivative changes its sign from negative to positive. It means that here our function has minimum, local minimum. We should remember about checking the way in which the first derivative changes its sign. Why? It is very important, and why we should remember about it. Because here we have the positive derivatives, here negative, and this is always true for maximum. So on the left, the function was increasing, on the right, the function was decreasing, because when derivative is positive for these x values, for the same range of x values, our function is increasing. Function is increasing when the first derivative is positive. Function is decreasing when the first derivative is negative. Therefore, this information about the way in which the sign of the first derivative changed is a crucial information when we want to identify the type of extremum value which was identified using the first necessary condition. And it was the first method which we can use when we want to find x values for which local extrema exist. So always we should remember, first to calculate derivatives, after it to solve a solution derivative equal to 0, to solve equation derivative equal to the first derivative equal to 0. Next, we should check the way in which the sign of the first derivative changed in these points which were identified. Maybe now we will make a short break. 5 minutes, I think it will be enough. So 15 minutes past 6, we will continue. Good evening again. So I'm going to continue. Using this method, we tried to solve our problem. We tried to find local extrema. I showed you the situation on this picture, but also I prepared a program which I used for generating this picture and for solving this problem. So my function, which here is represented by this blue line, is defined here. F is equal to x to the third power plus x to the second power minus 5 multiplied by x minus 2. It is a function. It is a function, and we are going to find extrema values for this function. What we should do? First, we should calculate the first derivative. It is here. Diff function I use for defining this function, and this function, the formula which has the first derivative, is displayed here. We see it here. 3 multiplied by x to the second power plus 2 multiplied by x minus 5. Using these rules which we had here, we can obtain the same results. But here, it was calculated automatically. So I have a function. I have a function describing values for the first derivative at a given point. And next, I should solve the equation. The first derivative is equal to 0. I solve this equation here, and the results are displayed here. Solution of the equation, the first derivative is equal to 0, and solutions are here. 2 points. Minus 5 third and 1. 5 third it is here, and 1 it is here. So we know points in which the first derivative is equal to 0. Now I'm going to check the way in which the sign of the first derivative changes. So I'm going to solve this inequality. The first derivative is greater than 0. I solve it here, and the result is here. The first derivative is greater than 0 for x belonging from minus infinity to minus 5 third, or for x belonging from 1 to plus infinity. Minus infinity to minus 5 third is here. It is this region, and we see that the first derivative is greater than 0, and from 1 to plus infinity, it is this region, and also we see that the first derivative, this orange line, is greater than 0. And also I solved the inequality. The first derivative is smaller than 0, and the results are here. From minus 5 third to 1. Yes, we agree, we see this region here on this range here on this picture. And I know that positive values of first derivative are here, negative are here. It means that at this point, the first derivative changes its sign from positive to negative. It means that the function was changes its character from increasing to decreasing. If the function changes its character from increasing to decreasing, it means that this point, this function has a maximum value. And of course, it is local maximum. And at 1, as I said before, the derivative changes its sign from negative to positive. It means that at the same point, function changes its character from decreasing to increasing, and therefore it is obvious that we have a minimum value here. And it was the first method which we can use. Of course, if I want to use this method, I must to solve some equations, maybe not some, but one equation and 2 inequalities. In this case, it is very simple, because this function which we have here in this presentation is very simple. But sometimes using this symbolic approach, it may be difficult. But the second way which we can use to solve the same problem, how to identify extrema, how to find minima and maxima. Of course, local minima and local maxima. Our function f has a local maximum at a point x max if the first condition is the same. It is necessary condition. If at this point the first derivative is equal to 0. And the second condition, it is a sufficient condition. If at this point the second derivative is smaller than 0. So now we must check the sign of the second derivative. It is enough to change the sign if it is negative or positive. It is not necessary to change the way in which it changes its sign. These conditions are for local maximum. When we want to find local minimum, first we should solve the equation that the first derivative is equal to 0, and to identify potential points in which we can have local minimum. And after it, at these points, which we identified during the first step, we should check if the second derivative is positive or negative. And if it is positive, it means that at this point we have minimum, local minimum. So for local minimum, the second derivative should be positive. For local maximum, the second derivative should be negative. The same function, which I use in our previous example. The function is presented by this blue line. Yellow or orange line, it is the first derivative of this function. Green, it is the second derivative. And first, I must find 0 points of the first derivative. So I must to solve an equation. The first derivative is equal to 0. I remember the results here. and here. And second, sufficient condition, I should check a value of the second derivative at these 2 points. Here, second derivative is negative. It means that the function, blue line here, has its maximum at this point. At this point, the first derivative, of course, is equal to 0. The second derivative is positive. It means that our function has a minimum here at this point. And the program is here. The first part is the same. I defined f function. It is the same function as I used before. After it, I calculated the first derivative. After it, I solve here the equation that the first derivative is equal to 0. And I found these values, which I remember from our previous example. Now I calculated the second derivative, and I calculated a value of a second derivative at points at which the first derivative was equal to 0. So these points for which the first derivative was equal to 0, I have here in this res vector, at the res list. It is a list with 2 elements. And now I'm going to calculate a value of a second derivative for x equal to the elements, to the first and after to the second element, which I have in this res list. And these values were displayed here. So for -5 third, a value of the second derivative is minus 8. It is negative. It means that for this value, we have, it is negative, so we have maximum. For 1, the second derivative is positive. It means that our function has minimum value at this point. It was the second approach, which we can use for finding, for identification extrema values for our function, local extrema values. Of course, we can do it when we are able to solve these equations, that the first derivative is equal to 0. When these functions are not very complex and we can find a function describing the first derivative. But this equation is the biggest problem. And here, because I use SymPy package, I was able to perform all these operations. Of course, I can do it manually, but sometimes it is difficult. So in practice, we use another approach. We use numerical approach. Because when I use numerical approach, it is not necessary to solve these equations, which I had to solve using this analytical approach, which I used here. So the last element for today, it is a short characteristic of numerical approach, which we can use for finding extrema values. I'm going to show you an algorithm which is called gradient descent algorithm. Gradient means the first derivative. Tomorrow, I'm going to explain why I use this word, why this word gradient is used here in this context. But here, because we are talking only about single variable functions, we can say that it is a first derivative descent algorithm. Today, I'm going to show you much more general approach in which we will have functions with many parameters, with many variables. And then derivatives are called gradients. But today, I'm not going to talk about it. I'm going to propose a numerical approach for finding extremum for a given function, local extremum, in a defined neighborhood of a starting point. It is an iterative approach. So we will perform some operations many times. For example, we have a function, very simple function, x to the second power minus 2. This line, this blue line, represents this function. And I'm going to find minimum value of this function. And my approach is the following. I know the function describing the first derivative. For this function, it is 2 multiplied by x. Here we have this derivative. And I don't want, or I'm not going to solve the equation, the first derivative equal to 0. I only know the definition of the first derivative. And I'm going to find an x value, a value which is located on this x-axis, for which a value of this function is the smallest. Of course, it is a very obvious problem, and I know that for x equal to 0, it is true. But please assume that we don't know that our correct answer is x equal to 0. So I'm going to find this value. First, I should start my process at one point which I can choose randomly. For example, I choose this value minus 2 as a starting point. And at this point, minus 2, we do not have a minimum value. But what I can do here, I can calculate a value of the first derivative. It is about minus 4. Minus 4, it is a value of the first derivative. Minus 4 means that the angle, the slope of this line, the straight line touching this graph, here, the tangent of this line is minus 4. So it means, when I think that you remember the shape of a tangent function, that it means that this function in this point is decreasing because tangent is negative. So it is a decreasing value. If it is decreasing in this part, so I know that the minimum value is located on the right. So I should go to the right. I should make a small step to the right direction. Gradient was negative here, is negative here. Negative direction is in here, and positive is here. So I should go in the direction which is opposite to the direction which is defined by a first derivative. First derivative here is negative, -4. So I can, of course, draw this arrow from this point to the -infinity direction, but I should go to the opposite direction. And I should go one step in this direction. Very small step. And I will move to, for example, to this point. And in this point, the situation is the same. The value of the first derivative is negative. So I should go to the direction which is opposite to a value of this gradient, to this, and this, and this, and this. And here, for example, the last step I move, making the last step, I move to this point, and here the first derivative is positive. The first derivative is positive. It means that at this point, our function has increasing character. That then now I should return, I should make a small step to the left because a minimum value is here. So I should make some steps to the right or to the left. Always the rule is the same. I should step a small step in the direction which is opposite to the value of the first derivative. And finally, I should reach this point which I have here, at which I have a minimum value. So it is the idea. The description of this algorithm is here. First, I should randomly choose the initial value, starting point. I should calculate the first derivative here, and I should move to the direction which is opposite to the value of the first derivative. Here, the first derivative function is, we have no derivative on this picture, but this function is decreasing. So the first derivative is negative. If it is negative, it means that I should go to the right. And we have the same situation, and finally I should reach this point. So choose randomly a position of a starting point. Calculate value of the first derivative. Change the x value. So here we should move to the right or to the left using the formula. X minus eta. It is rather small but positive value. For example, 0.01 multiplied by a value of the first derivative at the point x, y. And we should repeat this part many times. And on the internet, I found a program showing this technique. I made some rather small changes here, and I have this function. It is a function x to the second power minus 4 multiplied by x plus 6. Its derivative is defined here. Of course, I could use this SymPy package for calculating it, but I calculated it manually. And this procedure, which I presented to you, is here. So first, I should start from this point, which I use as an initial point. And here, I try to calculate a value of a first derivative. It is called gradient here. And here I calculated the new position. This eta value, which I have here is called learning rate. And I repeated it many times. And it is my function. This function, which is defined here, it is quadratic function, so it is very simple problem. And I started with x equal to 0. It is defined here. Eta is equal to 0.1, and maximum number of iteration, it is 50. And I can repeat these calculations. So we started from x equal to 0, and we move to this point, which we have, for which we have a minimum. It is 2. But we can check what will happen if I change this eta value. Now we check. The number of iterations was not sufficient. So we have not reached this minimum value. The algorithm stopped. Of course, we can change the number of iterations now and repeat. Also, it is too small. Maybe now. And now, possible to reach the optimal solution. So we see that the way in which our algorithm works, it is defined by these parameters, by starting point, by learning rate or eta value, and by the number of iterations. But it was possible to find this solution. But this problem was very, very simple. Here I have a copy of this program, but I defined another function. This function is defined here. Its first derivative is defined here. So the function is defined here. And I started my calculation at point x equal to 0.7. 0.7. So here I used this approach, and after some steps, I reached this minimum value. Everything is okay. Also, I can check if it is possible to find this value when eta is equal to 0.01. Yes, it is possible. But for smaller value, this algorithm stopped here. So it was not possible. The number of iterations was small. Also, we can check the results when eta is huge, for example, 2. I see that now it is not possible, maybe. It was not a good idea. Okay, but now because our starting point was here, 0.7. Now I will change it to 1.7. We started from this point, and also we reached this minimum. But now I will change the starting point to this point, minus 0.5. It is the biggest problem which I had here. We started in this point, and we found a minimum. But we found this local minimum. It is very small local minimum we have here. And at this point, our algorithm finished its work. It was not possible for him to leave this local minimum and to go to this point. So it is the biggest problem which we have with this numerical method which we use for finding minimum value. We should remember that we always can find a local minimum which is very close to a starting point. We change the starting point, and therefore it was not possible to find this solution. Please think about this blue function as about error function. It is obvious for us that we are going to find such values of x parameter for which we have the smallest error value. And if we if we start our calculations in the improper point, then it is not possible to find the best solution, the optimal solution. But of course, in this situation, we can draw this graph and we can see the shape of this function. And we can guess which is the optimal value at which we can start our calculations. But in real applications, when we have functions not with one parameter, but with, for example, 1,000 parameters, it is not possible to present this function graphically. And we don't know where are our calculations. And therefore, it is not possible to find the best solutions. So this algorithm which I presented here, and some other algorithms which are similar to this algorithm, has some disadvantages. So they work properly only for convex functions. Convex function, it is a function which has a shape which is similar to this function. For convex function, we can choose any 2 points and draw a line between these 2 points, and this line does not cross a graph of this, presenting this function. This line which presents this function. For this function, it is true, because for any 2 points, you can draw a line which has no common points with this blue line. But for this, it is not a convex function, because you can choose 1 point here, 1 point here to draw a line, and this line crosses this blue line. So it is not a convex function. In this situation, this algorithm does not work properly. Of course, it can, but it depends. Always we should remember that it is possible only to find local extremum. And also, we notice that eta value has a huge impact on the results. And tomorrow, we will be talking about similar problem, but in the situation in which we will have function with many variables. That's all for today, and we will continue tomorrow. Thank you very much.